Okay, in this lecture I'm going to talk about a triple integral. So triple integral is a sort of extension of this double integral to a more high dimensional case. So let's briefly review what is a double integral. So double integral is basically talking about if we are going to integrate, we do integration over a certain area, over, say here is S is the area we want to integrate over, and fxy is a function, basically is a function defined for any point here. So we define fxy to associate that with that. Okay, we have a defined fxy. Okay. Now the double integral basically is to compute two integrations. So we can sort of write this one into two parts. One is this is called inner integration. The other one is called external integration. So the integration part is not difficult as long as we know the lower bound and upper bound. So typically the lower bound for this guy, for the inner one, this is a function, some function of y here. Could be a function, could be a constant, of course, not a function of y. This generally could be a function of y, lower bound, upper bound for the inner integration. So for the external integration, typically it's just some numbers you have. Typically you have like some number a and b. Okay. Now if we move one more dimension to the triple integral, we're talking about integration over some 3D space. Okay. For example, here I give a 3D space. It's a basically cube, and the length on each direction is just 2 and 2 and 2. So I have along x-axis is 2, y-axis 2, and the z-axis 2. It's like a cube. Okay. So assuming if I know the density for each point, if I know the density for this 3D space, okay, at any point over here I can define basically say a function fxy, which will represent the density at this point. Now, in order to compute the mass of this object, 3D object, so we can compute this, what do we call triple integral? This is called triple integral. So typically, triple integral, talk about you have a 3D object, you integrate over a 3D object. So rather than 2D area, this is a 3D object. Okay, so you have triple integral. So in order to compute that, we follow pretty much the same idea as we mentioned for the double integral. The only difference is we have 3 integrations rather than the 2 integrations. We have the inner one, we have the middle one, and we have external one. Okay. So as I mentioned before, so similar to the double integral, so we also have, as long as we figure the lower bound and upper bound of all the integrations, and now we should be able to figure out we can calculate the triple integral fairly straightforward. Of course, this can be complex because we could have very complex functions over here. Okay, so generally speaking, following the same rule I mentioned before, generally speaking, for the inner one, the lower bound, upper bound are determined by whatever variable is outside. So here, this lower bound, upper bound could be a function of y and z. Okay, if you go one more layer over here, is the middle layer. So for this y, if you consider lower bound, upper bound, lower bound, and this is lower bound, upper bound, typically it's a function only the outside one, it's a z, because I don't care about the inside one. Okay, because I already first integrated inside one, I don't have any x anymore. So I could have the lower bound and upper bound for y could be a function of z. So here we generally have sort of y, z, and y under bar z and y bar z. That's lower bound, upper bound. It could be a function of z. Of course, it could be just a constant number. The external one typically is just lower bound, upper bound. It's just numbers. You don't have any function over here. Okay. So the key problem is trying to figure out what is the lower bound and upper bound for x, y, and z. Okay. For example, if I look at for this case, if I'm giving you this is my 3D object, so I'm going to compute trying to figure out the lower bound, upper bound for the x, y, z here. What are the lower bound, upper bounds? Okay, so if we start with z, because z only cares about the lower z only, we go to the external. This is z external one. It only tells me, just tell me, okay, what z I can select, okay? Okay, because it's starting from 0 to 2, right? It's just stating this cube is starting from 0, z0 to z2. So anything below that, anything below here, above here, you don't have anything, right? The street doesn't occupy this area. So basically, your z has to be from 0 to 2, which is pretty straightforward. Now, once you do that, you basically, for the inside one, what you do is you say, hey, if I give you some z, let's assume I give you some z over here. Let's say I give you certain z. This is my certain z value. I want to fix the z to see, hey, how the region. You basically have for this one you can consider as a double integral. So I want to see, hey, what is the area looks like for the double integral if I fix my z. Of course, this area could be a function of z, which means as z changes, as your z move up and down, now your area could be different. For this case, it's not different because it doesn't matter which z I select. If you select here, it just makes it to be constant. So your x, y will span this area, for example, this area. Okay. If you check another z, you can do different one. So this area is always what? So if I draw this one out, so your area, if I look in the x or y domain, so if I for certain z, because z is constant, you're only looking at the x or y domain. This is the x or y domain. So look at this one. So your region is given by this. It doesn't matter which z you have. It's always, this is 2, 2. This is also 2, 2, right? Because I cut across this, let z to be constant. You make you basically get a cut across this cube when setting z to be constant, right? So you always have this as the region for x or y. Okay, so it always starts for x start from 0 to 2, y also starts 0 to 2. That's why this one from 0 to 2 and also from 0 to 2. That's how you figure out the lower bound, upper bound for x and y. Okay. Now let me give you an example about how to compute this. Okay, let's just use this one. I give you set up some function f(x, y, z) for this case, for this 3D object. I want to compute the triple integral. Let's see, I have this f(x, y, z) is z. Okay, I want to compute what is the triple integral. And as a matter of fact, the computation is not very hard. Okay, the triple integral, as we already mentioned over here, is lower bound, upper bound, and lower bound are already determined. Okay, all I have to do is just replace my f by this, what I already defined over here, z. Okay, so if I do over here, I just do the integration. So integrations, there are 3 integrations. This is the first one, you integrate over x. The second one, integrate over y. And last one, integrate over z. So this is the 3 integral that I have to compute. So let's start with the first one, the inside one, inner one. Okay, so the other one that we don't change. So dy dz doesn't change. We just integrate over x. So z integrate over x, because z is not a function of x. Integrate over x is just z times x, and of course evaluate at 0 and 2. So this will give me z times 2 minus z times 0, give me 2z. Okay, then I start to do the second part. Okay, the middle one, which is over here. Okay, so this integration, because 2z again is not a function of y, so it's the integration of 2z over y is 2z times y, and evaluate 2 and 0 and 2. Okay, so and then after compute that out, I have 2z times y is 2 is 2z times 2 is 4z minus 2z minus times 0 is 0. So I have 4z. Okay, so then last integration will be the last part. The external one is integrating from 0 to 4z over dz. So integration of 4z over dz is just 2z squared, and evaluate 0 and 2. So this will be 2 times 2 squared minus 2 times 0 squared. This is 8, and this is 0, so this is 8 minus 0 is 8. Okay. Okay, this is the first example. Now let's go to another example, which is a little bit more complicated than the previous one. Okay, so for this example, I give you a 3D object which is given by this. Let's first define what is a 3D object I wanted to compute. Now the 3D object is defined by this object. So I have 4 points defined as a 3D object. So I have point 0, 0, 2. You basically have a point along on x-axis at point at 2 at z is being 2. Also at another point as a point on x-axis when x is 2, and also another point when in the x-o-y plane. So this point is 2, 2, 0, okay, which means this line is, you have 45 degrees, but basically you separate you have equal x and y on this line. The last point is 0, this point. So I have this object is defined by this object. I'm going to write up here, this one, this, okay, and then draw here, over here. So this is my 3D object, okay. Assuming this is my object, okay, and I'm going to compute the integration of z, okay. I'm going to still have f, x, and y, and z is z over here. So I'm going to compute this triple integral of z over d over this area v, okay. This is v, okay. This is v area I'm talking about, okay. Again, the key question becomes, how do I figure the lower bound, upper bound for x, y, z on the computer integrations, basically, okay. So here's how I will compute the lower bound, upper bound, okay. So again, let's first start with the z, okay. The z basically is whatever z you can select, okay, because I'm z starting from the bottom one is just the x or y plane, so which means 0, this is 0, okay. If you go up, you go here, this is the highest one you can reach. If you go up above that, you have nothing, okay. So which means the z is from 0 to 2. This is very easy to understand, okay. The next part is I'm going to fix z, trying to figure out, hey, for any z, if I give you z, what is my lower bound and upper bound for x and y? So this is a little bit tricky, okay. I'm going to do over here. So I'm going to use this figure to explain what's going to happen. So let's say I pick a z point, some z, okay, has to be true for any z, right? Now what is this triangle? What is this x or y looks like? What is the area, like 2D space I have? Basically I have 2D times 2D space, okay. So this one, the inner one, try to figure out this is like the double integral. So basically want to figure out, hey, what is my lower bound, upper bound for my double integral? Of course, this can be dependent on what z value we have, okay. So for different z, as you can see over here, if z, okay, doesn't matter what z we selected, this always has this shape. If I took this one x or y plane, so I look from the top to bottom, so what it looks like here is always have this shape. It's like this one, and this is always the shape. Of course, the size can be different because for different z, the size can be different, right? Because this is the bottom one. If you could move up, it becomes smaller, right? Basically, okay. So what I'm trying to do is, hey, let's look at this. What is this related? What is the size if I give a certain z? So if z is 2, you have 0. You basically the size 0. If z is 0, so this length is 2, right? Because it's a linear relation, this is a straight line. So linear relationship. So you start from 0. If you're 2, you got a 0. If you're 0, you got 2. So you basically, the length of this x is determined by 2 minus z, right? Because z is 2, you got 0. Z is 0, you got 2. That's why it's this relationship. Because linear one, so you must have this one. So the length is 2 minus z. Of course, this length is the same, right? This is also 2 minus z. And also this is at 90 degrees, so perpendicular. This is the line which tells you that x and y to be the same if you're on the line. Okay, so basically for different z, I have different lengths. So the length here is 2 minus z for this length. This is also 2 minus z. 2 minus z, okay? So I have 2 points. Basically, the area determined by the origin. 2 minus z is 0, and 2 minus z, 2 minus z. That's define my area. Okay, so if I give you this area, now we can figure out what is the lower bound, upper bound for x and y. Okay, so let's start with y. Okay, so start with y. Y can be from 0 to, y can move from this line up to this line, right? So y can be from 0 to, this line is, oh yeah, this is basically is a 2 minus z, right? 2 minus z. That's why y is 0 to 2 minus z. Now for what is x? So x means, oh, for a different x, if I select certain x over here, what is my certain y? Sorry, it's a different y, certain y. So what is my lower bound, upper bound for my x for this defined region area? If you do this one for y, okay, basically you're going to start from here to this point. So your upper bound is always 2 minus z, basically, right? You already start ending here. Your starting point is from y, because whatever y define the lower bound. If your y starts from 0, your x will start 0, right? Because you're going to cross this line. If your y start from 2 minus z, you got 0. That's why it's starting from y to 2 minus z. Okay, that's why you figure lower bound for x is y to 2 minus z. So y, lower bound for upper bound for y is 0 and 2 minus z, and z is from 0 to 2. Okay, so that's the way we figure out the lower bound and upper bound for y, x, y, and z, basically. Okay. Now, once we do that, all the computation just becomes just do the computation of the integrals. Okay. So again, we start with the inner one. We do the dx integration only. Okay, the first step. You do that one, we'll keep the outside to be the same, so that's will be the same. So integration of z over x again is z times x, and the value of 2 minus z and y. Okay, and then we evaluate the values. This value becomes z times 2 minus z minus z times y over dy dz. Okay, we do the double. This becomes double integral, and then this one we move to this integration. Okay, so this sign will keep the same. The inner one of this one, we do a little change of this one. This one becomes negative z squared plus 2z minus zy. So the integration will be just the negative z. This guy is not function y, right? So it's just negative z squared plus 2z times y. This one is negative z times y, which is negative zy squared divided by 2, basically, right? The value is 0 and 2 minus z, okay? And keep following, do the computation, okay? If you do that one, you substitute this y by 2 minus z. 0 doesn't appear because minus 0, minus everything times 0 will be 0, right? So do the whole stuff over here, and it just becomes function of z. And integrate from 0 to 2. And if we do further more step, okay, we just clean up a little bit, and we just do the product. It's just z cubed minus, so this is z cubed minus 2z squared. Then this is plus 4z minus 2z squared. What's this? This guy becomes z times z squared minus 4z plus 4. This time just do the product. So if you look at this one, so this is, if you do the product, this two, this, because this will keep this, I just put them together. It's z cubed minus 4z squared plus 4z. This one is z cubed minus 4z squared plus 4z. So this one, okay, look at this one. This one and this one, they're the same. This is just by a half. So this guy minus the half is just this half, right? The half. So it becomes a half. And if you integrate the half, it's just integration of this z cubed is just, I move the 1/2 outside. The integration of this guy will be just 1/4 of z to the 4th minus 4 divided by 3 times z cubed plus 2z squared. Okay, do all the integration and evaluate 0 and 2. So this is just 1/2. I just replace everything, as the z by 2. And this is minus 1/2. I replace everything by 0. It doesn't matter, so it's still 0. That's why I ignore this part. Now I do some cleanups and do all the calculate this value, so this becomes 2/3. Okay. So to summarize, the key point to compute the triple integral is try to figure the lower bound, upper bound for all the x, y, z's. So here's my suggestion that how you can figure lower bound, upper bound. So first of all, the lower bound for the very last one, you can swap the order if you want to, but for the last one is only depending on what is the lower value, the smallest value, the highest value. For this 3D object, what is the lower value and the upper value of this this value can select. For example, for this 3D object, the minimum you can select 0, the upper is 2. Okay, above and below that you don't have anything. The 3D object doesn't occupy any area. Okay, then after doing that, you just let z to be, assuming this is some value. Okay, some value you have. You try to figure out, hey, what is the 2D space I have integrated for this inside one? Okay, for this one. Okay, of course, this is 2D space can depending on what actual z value you have. For example, here. So once you do that, you're trying to do just in the 2D space. Okay, trying to figure what is this area I'm going to integrate over for a given z. Okay, so you figure out this area, then you try to figure lower bound, upper bound for the double integral, which we haven't talked about before. Okay. So I hope this will be helpful for you to figure out the lower bound and upper bound. After doing that, the computation should be fairly straightforward. Of course, it can be complex.